Okay, so any questions about this? Okay, so I think we're doing pretty good this semester, time-wise. So yeah, this Thursday, tomorrow, you guys are going to do, basically take copper through a series of chemical reactions. So there's nothing edible at the end, but you will see some kind of interesting things to observe along the way. It gets harder and harder to like wow you guys too in this day of electronic gizmos, but I like this one. Let's see what you guys think. Tomorrow's lab, we'll be using the Bunsen burners. No, everybody has to have their foot covered, okay? No open-toed sandals or anything. Otherwise, you can't do the lab. And this just goes without saying, you know, as it gets warmer and stuff, especially people who look good in them, to kind of show your belly button, that's probably not a good thing to wear either. I don't know if anybody wears those. But especially kind of where the black top or the tabletops are. And looking ahead then, we'll start Unit 5 material then, that Friday, okay, after your test. And then actually the Unit 5 is going to be gases, but there is no Unit 5 exam, but there will be Unit 5 questions on your comprehensive final. Okay, well that's that. In the meantime, we get to continue on with the whole balancing equations thing, okay? So you guys spent some time putting those stoichiometric coefficients, the right one, in front of the species to go ahead and to get the same number of atoms on either side of the reaction arrow. You balance your chemical equation. Non-balanced chemical equations are great, though, too. So what stoichiometry does for you, it's a type of math problem. It's a really common type of math problem in chemistry. And what stoichiometry, or what the stoichiometry of a chemical reaction is basically you look on the reactant side, arrow, you look on the product side, okay? And basically the stoichiometry is kind of the relative amounts there are going on in your chemical reaction, as indicated by your balanced equation. So stoichiometry can only work if you've gone ahead and balanced it with the stoichiometric coefficients. That's the only way stoichiometry can work. Okay, and if I'm looking for a vocab word, this one screams, this is a legitimate vocab word. Okay, so stoichiometry is kind of amounts. And so stoichiometric calculations is amounts. So if we go back and pick on the one you guys did in lab where you guys burned your magnesium ribbon in your crucible, okay? This is balanced if we go with coefficients of if we go with coefficients of 2, 1, and 2 across the board. We do have the same number of magnesium and oxygen atoms on either side of the reaction arrow, like we talked about on Monday. So to me, when I balance it, I usually think of it, these coefficients of 2, 1, and 2 as being on the small scale. So I usually think of basically 2 magnesium atoms react with 1 molecule of O2 to form 2 formula units, because magnesium oxide is an ionic compound, to form 2 formula units of magnesium oxide. But as I kind of mentioned with those fractional stoichiometric coefficients, when we do stoichiometric calculations, we kind of need to scale it up and think of those coefficients of 2, 1, and 2 across the board as not on a small scale, but as on a large scale. So on a large scale, what we mean is we have 2 moles of magnesium reacts with 1 mole of O2 to form 2 moles of magnesium oxide. And remember what a mole is, guys. And, you know, your final in here is comprehensive, so you're going to want to remember what a mole is. Okay, 1 mole of anything is 6.022 times 10 to the 23rd of that anything. Hockey pucks, atoms, molecules, okay. So we are scaling these up. And here in a minute, what I'd like you to kind of think of it this way, I always look each semester kind of a different way to maybe teach this. You know, this is basically, I'll put R for reactants here, right? P for products over here, or one product, okay. We could kind of say in terms of moles that in this relationship, for instance, 1, oops, I better put 2. Since the coefficient in front of magnesium is 2, we could say 2 moles of magnesium is equal to, for this reaction, 1 mole of O2. Do you see where I got that? The 2 is from this 2, okay, and this 1 is from this implied 1 right here. I know it sounds weird. You're making an equality statement. 2 moles of magnesium is equal to 1 mole of O2. How did I get that? From this balanced chemical equation, okay? I could go ahead and that's the stoichiometry. That is the stoichiometry of magnesium reaction with oxygen. So let's pick on one more before we move on. I could also make another equality between the magnesium again, so 2 moles of magnesium, and I could do a stoichiometry with the product side is equal to 2 moles magnesium oxide, right, for this chemical reaction. And you know what we do with the qualities? Okay, we turn them into ratios and use them as conversion factors. So that's exactly what I'm going to do next. Okay, so when you balance those equations that represented reactions, when you put coefficients in front of the species to get the same number of atoms of everything on both sides of the reaction arrow, okay, you ended up with relative amounts in terms of small-scale particles, atoms, molecules, formula units, and or relative numbers of moles. Okay. So the calculations, the classic stoichiometric calculation is going to go like this. Basically, you're going to go from the amount of something to the amount of something else. And those two somethings could be both reactants. Those two somethings could be a reactant or product. Those two somethings could be both products, okay? But that's what stoichiometric calculations are. And usually, you're going from grams of something to grams of something else, usually, okay? But actually, we're going to start out with moles of something to moles of something else, just to make it a little bit easier. Now, this is a new slide for me. You guys don't have this. A lot of times, I talk about how stoichiometry and a chemical equation, or excuse me, chemical equation, stoichiometry and chemical equation is kind of like a recipe. Those stoichiometric coefficients you put are kind of like a recipe. So I thought I would go ahead and go out on the internet and grab a recipe for brownies. I hope everybody's eaten, because this might make you hungry. So for this recipe, you know, if you're making brownies, and I don't know if I'll show you this short video, but I did go ahead and and Alton Brown is like he's a Food Network dude. And I don't know how popular he is now, but he used to catch my attention years ago because he was like into chemistry. But I Googled him this morning. Apparently the dude failed, I don't know if this is right, but he apparently failed high school chemistry and college chemistry, so I'm not sure. But a lot of times he'll stick in kind of what's going on behind the scenes. So my thing about this recipe being kind of like a chemical reaction, I bet you guys buy this. So I'll just pick on a few ingredients. I could say that 4 eggs, okay, plus 1 cup sugar. I'll pick one more. Plus other stuff, but let's see, plus 8 ounces of butter. Butter. Okay, we'll give you, right, those are ingredients. We'll give you, we'll pick on how much it'll give you 8-inch square pan. I'm making this up as I go. 8-inch square brownies. Okay? Does that seem right? Right. And so I could actually kind of put squiggly marks under my 4 for my 4 eggs, 2 cups for my sugar, 8 ounces. Okay. So that's like the relative. That's the stoichiometry of the recipe. So I could say, just like I said a minute ago, I could say for this particular recipe, 4 eggs is equal to, or will give you, I'll put 1 8-inch square of brownies. Okay? put a coefficient of 1 in front of there. So here's the deal then. Do you see where I could say something like, I'm going to go ahead and take that equality, 4 eggs is equal to 1 8-inch square brownie. I'm going to go ahead and make that a ratio. Here in a minute, we're going to call those stoichiometric ratios. But just for now, I'm going to take that equality and do this to it. Let's see, which way do I want to go? I'm going to put, I'm going to put 4 eggs per 1 8-inch square brownie. Okay. There's a 1 in front. That's not 18. It's 1. 18 square. 1 8-inch square brownie. So here's how this works. And I've gone a long way about this. But let's just say you wanted to scale it up. And let's just say you want or you need, let's see, we're making it for an army. Let's say you need 5 8-inch square brownies. Okay, let's say that's what you need or what you want. Here's how the problem would go. Basically, you would start out with with what you want, which is 5 8-inch square brownies. And do you see where if I go ahead and take this ratio down here, I can insert it here, and I run out of room. But if I insert it there, do you see where my 8-inch square brownies are going to cancel? Okay, and I'll be left with what, eggs? So if I take 5 times 4, I'm just going to go ahead and put the 4 eggs per every 1 8-inch square brownie. Those cancel. This is my eggs. So if I was scaling up that recipe to 5 times, you guys would say, "Oh, I know. I take 4 times 5 because I'm pentacling the recipe, not doubling. I'm taking it times 5, and I know I need 20 eggs. But here now, you know you need 20 eggs. Okay, there you go. That was my first go at this, taking a real recipe off the internet. So let's go back to my slides. Okay, so that whole deal of taking an equality and making it into a conversion factor, that conversion factor is a ratio. It's called a stoichiometric ratio to work stoichiometric calculations. And the way I get those numbers for the stoichiometric ratio, and the reason I'm emphasizing this is because down the road students get it confused. But where those numbers came from were the coefficients in the balanced chemical equation. That's going to be your stoichiometric ratio. How do you know what goes on top and what goes in the bottom? It depends upon what you start with. It's kind of like we did use ratios before. What you start with needs to cancel, and you want to be left with units that you're after. So it's we just continue to come back to this factor label method. All right. So here we go. We could say that 2 moles of magnesium is equal to 1 mole of O2. And from that equality, we could come up with 2 ratios. Here they are. Those are my 2 ratios. We're going to have to use those stoichiometric ratios depending upon what we're given and what we want to get to. Can you see where the first one is if I was given moles of O2? Okay, if I was given moles of O2, I wanted them to cancel, I would use that one. And if I wanted to get to moles of magnesium, that's what I would use. Okay, so this is given and want, or get to. Same thing with the next one. So I've got actually 6 ratios up here. This ratio is linking magnesium and the product. Okay, a little bit ago I said for these coefficients of 2, 1, and 2, we could pick on magnesium and magnesium oxide. We could say 2 moles of magnesium is equal to 2 moles of magnesium oxide. A lot of times students will say, well, Mrs. Snipes, can I go ahead and reduce that 2 over 2 to 1 over 1? You can, but you lose a little bit of information. And of course, the last thing is we could pick on the oxygen and the magnesium. So their stoichiometry between the oxygen and the magnesium looks like this. 1 mole of oxygen is equal to 2 moles of magnesium oxide. We come up with 2 possible ratios. So if you would label this A, B, C, D, and E, and F. Because we're going to do a problem with this equation. We're going to do a stoichiometric calculation. Okay, 2 stoichiometric calculations. Here's the first of our 2 stoichiometric calculations. So we're going to use either A through F, okay, to knock out this problem. So it says how many moles of oxygen. Okay, how many moles of oxygen? So actually, if I were diagramming that, this would go over here like this. Moles of O2. How many moles of oxygen? Thing in brackets is optional. Are needed to react with 2.45 moles magnesium. Okay, oxygen and magnesium. To me, it's looking like A or B. You buy that on the previous slide with the 6 ratios? Okay, how many people think we want moles of magnesium to cancel when we want to be left with moles of oxygen? How many people think we're going to go with A? How many people think we're going to go with B? B it is. Very good. And we're going to be done. The next one we're going to work through is we want to get to moles of magnesium oxide. Now this one, the wording on question number 2 probably could be improved. There's a lot of things that probably could be improved. But this is assuming that, you have this, assuming you have 0.245 moles of magnesium. I'll usually on a test be a little more hitting you over the head with that. So in this case, how many moles of magnesium oxide? So that moles of MgO go over here. When I say MgO, I always think of B-I-N-G-O. MgO, I know. Anyway. So how many moles of magnesium oxide can be produced from 0.245 moles of magnesium? So to me, it looks like on the previous slide that we're looking at, what, C and D? Okay? So we want moles of magnesium to cancel again. We want to be left with moles of magnesium oxide. How many people think we're going to use C? How many think we're going to use D? Very good. All right, so let's knock these out. So the first one, we're going from moles of magnesium to moles of oxygen. And like you said, we're going to use B to get there. That's kind of how we're diagramming it. It's like we worked other factor label problems before. The thing we want to start with is going to be the thing unique to the problem, the thing we want to convert from. So it's going to be your moles of magnesium. Okay. Oh, sorry, and then that's for problem 1. The strategy for problem 2, you guys said that we're going to use D. And so here is D. You were right. So now let's knock it out. Okay. In both cases, we're going to start with that 0.245 moles of magnesium. I would usually put this over 1, even though my slides don't do it, because then we can insert that ratio you guys told me, 1 mole of O2 to 2 moles of magnesium. The moles of magnesium will cancel. Units of moles of magnesium will cancel. We'll be left with units of moles of O2. There's no uncertainty in those stoichiometric coefficients, so we only have to round according to the thing we want to convert. There is uncertainty in that 0.245 moles, so we need to round according to 3 sig figs. Okay, so 0.123 moles of O2 is what we got. So I'm going to switch gears here in just a minute, and we're going to kind of well, how do I say this? I guess I'm going to assume that we're all on the same page. So do you guys see where this 2 came from here, okay, and this 1 came from here? Are we all good with that? All right. Well, the next one shouldn't be too bad. So it's the same setup. We have, again, that 0.245 moles magnesium. I probably put that over 1. And now we're going to use that 2 to 2, or 2 moles of magnesium oxide to 2 moles of magnesium. And yes, you get the same number, right? But as silly as it may seem, I'm going to have to see you work it this way. This is the whole thing of factor label method, is that the labels factor out, the units factor out. So moles of magnesium cancel. We're left with moles of magnesium oxide, and that's it. So here are a few problems. This is called a moles to moles problem, but and it's stoichiometry. It's like relative amounts. I think we can kind of see that. But usually chemistry problems are grams to grams. Okay, so we have to add something a little bit to what we're doing there. So here is what 17, 29, and 30 look like, if I can find it. We are... What if I put it in my folder down here? Hopefully. So here's 17, moles to moles problems, okay? So notice that in this case, we have 4 problems you're going to do with the same information. So let's see, calculate the number of moles NO2 on each reactant. Okay. So in all cases, you are going after the moles of NO2. Okay, like for instance, in this case, you're assuming that you have 1.3 moles of N2O5. Okay, so I usually put a question mark, moles of NO2. So if we just kind of look at this based upon what we were doing earlier, the stoichiometric ratio to accomplish this, we're going to want moles of N2O5 to cancel, so I'll put those units down there. This is usually how I do it, N2O5. We want to be left with moles of NO2. I leave the number blank. I generally do. That's the ratio we're going to use. Why? Because that's the units we need to use. So now, in order to know what the numbers go in there, we have to go clear up to here. I guess it's not clear up to here. And it looks like we're going to put a 4 in there. And we are going to put, what are we going to put for the N2O5?
2.
A 2. Okay? So I don't want to do your homework for you, but that's basically how you do A. Okay? Looks like this, and I'll post that on the Twitter feed. Notice that 29, they say it's unbalanced. So first you have to balance it. And I didn't do this for you guys, but notice you have to balance it first. I'll put it in red. And then it's similar to the other one. So A says to balance it. How many moles of silver nitrate are required to completely react with 9.3 moles of lead? So if we were diagramming B, it looks like this. How many moles of silver nitrate, question mark, moles, silver nitrate, AgNO3, are required to completely react with 9.3 moles of lead? Okay, so I'm just going to kind of leave that for you guys. You're going to come up with a ratio that gives you units of moles of silver nitrate, and in the denominator will be moles of lead. The last one looks like this. Again, A says to balance it. Okay. B says, let's just kind of look what B says. Okay. After you balance it, how many moles of H2SO4, question mark, moles H2SO4 are required to completely react with 8.3 moles of aluminum? Okay. So you're going to come up with a ratio. Again, after you balance it, you'll know what goes in these circles. But you know that you want units of moles of aluminum to cancel, and you know you want units of moles of H2SO4 to be left. So only after you balance it can you put in those circles. Okay? It's fun. All right. So let's take a look. Let's keep going. So those will be due on Friday. So I want to take it up a notch. That was a moles to moles conversion, moles to moles stoichiometry problem. But usually it's grams to grams, and that's exactly what we have in these next two problems, dealing with the same chemical reaction. So what mass of oxygen is needed to react with 0.30 grams of magnesium? So let's just go ahead and kind of start, and I have a full diagram here in a minute, but can you see where here, there's going to be a few steps in between. Let's see, what mass of oxygen, question mark, grams, O2, okay, is needed to react with, over here at the first part of my strategy, we have 0.30 grams mg. So that's kind of what we have going on. So I was trying to think of a good way, we looked at the brownie recipe, and I'm like, how could how could I make this analogous? Oh, I know. In the brownie recipe where they had there was ounces of chocolate, there was whole eggs, there was cups of flour and sugar. Well, what if we kind of didn't use, for instance, the units with the the cups of flour, or pick on flour, and I know that the chocolate was in ounces. So it's 8 ounces of chocolate. Okay, there's an 8 there, and 1 cup of flour. There's a 1 there. So what if we just went 1 and 8 as their without the units, without we don't care. Okay. No, they're only related by ounces of chocolate to cups of flour. Just like these things, the magnesium, oxygen, magnesium oxide, those numbers only relate relative number of moles. They do not relate relative grams. They do not. It would be like kind of scaling up your ounces of chocolate and your cups of flour. Okay? So, what we did before to go between magnesium and oxygen, okay, that was a moles to moles problem. We could use the stoichiometric ratio B that you told me. That was awesome. But we cannot use that same ratio to go straight from that 0.30 grams of magnesium to grams of O2. You cannot. Okay? Grams won't cancel with moles, right? So what we're going to have to do is actually something that we've been talking about in Unit 2 and Unit 3. So what we're going to have to do is go from grams of magnesium to moles of magnesium. We can do that by stuff we talked about actually back in Unit 2. How do you get from that 0.30 grams of magnesium to moles of magnesium? Using magnesium's molar mass, which I love to say that one too. Magnesium's molar mass. And that was one you just pick off the periodic table, right? But you have to do this kind of front end conversion. And then that middle stage, actually that middle stage is back to what we did already this morning. That middle stage, when we have moles of magnesium, to go ahead and to get to moles of O2, all we got to use is that B stoichiometric ratio. And then to finish off, okay, at that point we'll have moles of O2. To finish off, to get grams of O2, we're going to have to use O2's molar mass. Okay, so that would be what? The decimal number of oxygen times 2. Now, one of the things I'm gonna have you do on all calculations, not only show all of your work, well, in showing all of your work, also show how you got to your molar masses. This is a really common pattern of how you do things. Okay, basically, we have the grams of what you know, okay, molar mass of what you know, in this case, the magnesium, okay, let's see, oops. That would get you moles of what you know, okay, and then you get to moles of what you don't know, moles of moles. In this case, the O2, I'll put unknown quantity, using the stoichiometric ratio, like you could do for your homework for Friday. And then we get to grams of the unknown. That's really ugly, using the mm of the unknown. You'll do this a few times, right? So basically we have 2 molar masses, okay, and 1 stoichiometric ratio. Whew. I'm glad I don't write everything. All right, so here I have, and you guys are quite capable of doing this, but I went ahead and did it for you. I don't know if it's already on your slides. Here are the molar masses of everything that you'll need to work these problems. So the molar mass of magnesium is simply picking off the decimal number for magnesium from the periodic table, 24.31 grams per mole. The molar mass for O2 is taking 2 times the decimal number for oxygen, so it's 32.00 grams per mole. And the molar mass of magnesium oxide is taking 1 times the decimal number for magnesium, which is 24.31, plus 1 times the decimal number for oxygen, which is 16.00. So these are the molar masses. So sometimes if you want to think of it this way or even write it, like for instance that magnesium oxide, it's really 24.31 grams per 1 mole. You know, kind of getting it ready to use as a conversion factor. The oxygen, 32.00 grams per 1 mole. Magnesium oxide, 40.31 grams per 1 mole. And actually, as we start doing these stoichiometric calculations, since we have a known, which is magnesium, and an unknown, which is O2 in this first case, a lot of times we'll go ahead and be explicit. So for the first one, I would put 24.31 grams of Mg per 1 mole of Mg. For the second one, 32.00 grams of O2 per 1 mole of O2. And for the last one, it's dealing with magnesium oxide. That's what I call being explicit. And actually, that's probably a better way to go right now. All right, so that's kind of the legwork on the front end to work this problem. Okay, so remember our strategy is to start with the mass of the known, which is magnesium. I usually put it over 1. And can you see on the previous slide, we can use the molar mass of magnesium, but we want grams to cancel. So we're going to use what I call the flipped version of the molar mass of magnesium. Okay? So there's the molar mass of magnesium, the flipped version. So notice we do need to go ahead and be explicit. Sometimes students will want to break this sort of stoichiometric calculation up into 3 parts, and you totally can do that. I kind of like to just string them all up. But if we're keeping track of things that cancel there, okay, inserting the molar mass of magnesium, now grams of magnesium have canceled. Okay, we're left with units of moles of magnesium. Now's that middle step to get from what you know to what you don't know, which is O2. So we want moles of magnesium to cancel. We want to be left with moles of O2. And I usually put that there, and then I go back and look at their stoichiometric coefficients. So this is that ratio that we used before, where remember that the 1 came from the O2. Okay, don't lose sight of where that came from. The 1 in front of the O2 came from that right there. Okay, the 2 here in front of the mg came from that. Okay, so this is your stoichiometric ratio. All right. So can you see moles of magnesium will cancel at that point? We're left with moles of O2 and we're almost done. That's an amount, but we want it in grams of O2. So now if you look at the previous slide, we have the molar mass of O2. And since we want moles of O2 to cancel, we're going to leave it in the unflipped version. So that's why it's 32.00 grams of O2 per 1 mole of O2. And moles of O2 cancel. And the only units that we're left with are grams of O2. So yes, you do have to be explicit with those moles and grams. And so numbers bringing uncertainty would be the mass, that 0.30. Also, the molar masses bring uncertainty, but we've got 4 sig figs in the molar mass of magnesium, and we have 4 significant figures in the molar mass of O2. So it looks like we only have 2 significant figures in the molar mass of magnesium, so that's what we're forced to round by. Okay, so rounding to 2 sig figs, the mass of O2, it's like a recipe. Now finally you have scaled up from moles, which you really can't sink your teeth into, to something that you can go out and measure if you wanted to. Okay. Grams to grams. Well, let's knock out that second question. So I said that second question would have the same starting mass as the first one, that 0.30 grams of magnesium. Assuming we have, I will talk about what sufficient means, but basically it's looking like this. It says, all right, I got 0.30 grams of this. And anytime you see the word sufficient oxygen, I usually think of it in terms of extra. You have extra oxygen. So basically this green number, this magnesium, this 0.30 grams of magnesium, we're going to run out of that first. And so in this case, our question mark goes under the magnesium oxide. Okay, so to work this, we're going to start with the gram, what we're given are known, 0.30 grams of magnesium, usually over 1. The first 2 terms are the same, aren't they? The first 2 terms are the same for both of these particular problems. So we're on our way to grams of magnesium oxide, but we're going to have to go through moles in the middle. So we're going to take use the molar mass of magnesium to get the moles of magnesium. And then we're going to insert the stoichiometric ratio. So we want moles of magnesium to cancel. We want to be left with moles of magnesium oxide. Then we go up there to see what their stoichiometric coefficients are. And they're 2 and 2. So that middle term is your stoichiometric ratio. Notice the stoichiometric ratio has nothing to do with the subscripts. The stoichiometric ratio has only to do with the coefficient in front of the species. So moles of magnesium will cancel, and we have moles of magnesium oxide. We want grams of magnesium oxide, so if you flip back a few pages, or whatever, a few slides, we need to use the molar mass of magnesium oxide, and we want moles of magnesium oxide to cancel. We want to be left with grams of magnesium oxide, so we use the unflipped version of the molar mass, so 40.31 grams of magnesium oxide per 1 mole of magnesium oxide. So moles of magnesium oxide cancel. Rounding wise, it looks like we're back to 2 significant figures as required by the mass of our magnesium. So we get 0.50 grams of magnesium oxide. Now, if you're like, that's a nice round pretty number, and I maybe should have been able to get that to that. Do you see your 0.30 and your 0.20 in the previous problem? 0.30 plus 0.20 is equal to 0.50. And actually, that's what we call a mass balance, and it should be the case. It's a good way to check your problem. Could we have knocked out 0.50 grams of magnesium oxide even without doing that? Yeah, if we were confident in our other work. So it's more of a check than a way to do things. Okay. So that's good. I didn't quite know how far we'd get. I think we're just going to stop there. And actually, though, if you want to look at the homework, you can. That's going to be due on Monday. You should be able to do some of those. No, I think we're going to do what I'm going to do. I'm going to go back to what I was going to do. I'll show you what I was going to do. I think this will be a good thing. Okay, so here's the deal. If you go ahead a few slides, you can see an assignment slide, and I want you guys to do the first one and hand it in with your moles to moles conversions. Okay, 835 is due, and we'll take a look at it, but 835 is due Friday. There will be more that's going to be due on Monday. So here's what 835 looks like. It looks like this. Okay, it's stuff that we were just doing. And if you fumble with it, if you do it great, either way. Notice they balanced it for you. For the reaction, calculate how many grams of each product will form given the amount of each reactant that completely reacts. Okay, so for A, this is a good one. You guys know there will be some of these on your next unit exam a week from tomorrow. Wait, 2 weeks from tomorrow. Yeah, 2 weeks from tomorrow. Okay, for the first one, it looks like this. Okay, you have to read it a few times. I usually do. Chemistry problems are like this. Okay, calculate how many grams of each product. So actually, you're going to have to go for grams of aluminum oxide and grams of iron. Okay, that will form, in this case, starting with 4.7 grams of aluminum. So for instance then, it looks like this. We have, let's see, what color do I want to pick? 4.7 grams of aluminum. I'll go ahead and remind you that in this grams to grams problem, we're going to go to moles of aluminum next. And then we're going to go to moles of aluminum oxide. And then we're going to go to grams of aluminum oxide. Do you need the molar mass of aluminum oxide? Yep. Okay, so you're going to want to count that, calculate that aside. Okay? We said that to do the first step, you're going to use the mm of aluminum. To do the middle step, stoichiometric ratio. Do the third step, molar mass of Al2O3. So, but notice that for both of these, there is a second one, and the second one for A goes like this. Based upon 4.7 grams of aluminum, how much iron will you get? And so we're going to have to go from moles of aluminum to moles of iron to grams of iron. Okay? So one more thing. Those hints will be posted. Notice this stuff down here. I think I'll try to pay close attention. I'll actually grade your stuff. Sometimes I don't really grade your stuff. I just kind of put a 10 out of 10 on it, okay? But I'm going to be looking for this stuff. I'm going to be looking for you to show all of your work, okay? Show, I guess I'll go ahead and put a bullet here. Show, if I put MM, you know what that means. Show molar mass calculations. That's part of your work, okay, to get full credit. All right, that's all I have today. See you tomorrow in lab.